Okay, this is a solution for particle kinetics number 19. That's a problem that looks like this. You have a wall, a ceiling, a wall, and there's a pulley attached to each of these. And then there's a cable that goes over all these pulleys. And connects to a mass. The mass is 150 kilograms. And we're given the angles here are 40 degrees. And we are supposed to find the tension in the cable, I assume. Let's see. What are the two force vectors the cables apply to the mass? Okay, so not just the tension. The tension would be just a scalar value, a number, but we also need to come up with the directions. But the main thing about this problem is when you first look at it, it looks like a complicated problem. There's a lot going on. If you just follow the steps of how you deal with cables pulling on the object that you're isolating, it turns out to be a really easy problem. So I'm going to start with a free body diagram of the hanging mass. And first I'll deal with the weight force vector. 150 times 9.81 is 1471.5. And now just go around the boundary of this mass looking for where there's contact. The cable makes contact with it over here, and that's a pulling force. So we have a force vector T. We're going to have to figure out what that T is. And then that same cable goes through all the pulleys and ends up applying a force over here too. It's in a different direction, but since it's the same cable, the magnitude of that force is T. Okay. And now to put that in Newton's second law, all we need to do is represent these two force vectors as components. So we have the one that's in this direction, where this angle is 40 degrees. And we have the other one on the left. What happened there? Okay, we have the other one acting on the left. That is like that, okay? And the angle that we know is 40 degrees from the negative x-axis to that vector. Okay, so to one of these, to the one that's on the right side, the counterclockwise angle from the x-axis is positive 40. To the other one, it's 180 minus 40, so 140. And so now we can go to Newton's second law. We have the weight force. And then we have, I'll do the one on the right side first. So that's T times cosine and sine of 40. And then the other one, the angle we're going to use is 140. So T times cosine and sine of 140. And then the last thing we have to do is set that equal to the mass times the acceleration. This is just hanging in place. And so there's no acceleration. And so this just ends up being 0, 0. All right, so we get two equations. The x equation says 0 plus 0.766 t, that's t times cosine of 40, plus t times cosine of 140, which is negative 0.766 t, is equal to 0. Okay, so that one doesn't help. That just gives us 0 equals 0. But the y equation is not going to cancel out, and that will give us something useful. That says negative 1471.5 plus 0.643 t. Sine of 140 is also positive 0.643 t, so plus 0.643 t is equal to 0. And now you just have to solve for t, and you get 1471.5 divided by 2 times 0.643, that's 1.286. And so you get t is equal to 1,144.25 newtons. And that's basically it, except that we're supposed to give these force vectors, not just the magnitude of the force vectors. Well, we've already figured out the force vectors as components. They're expressed in Newton's second law here. You know, you can, if you can see my cursor here, the one I'm circling, we'll just plug the 1144.25 into that, and that's the force vector that's applied to the mass by the part of the cable on the right. The other one is the, multiply by 1144.25. That gives you the force vector applied by the cable on the left, and you're done. So let's see. So the force vector on the right is 1144.25 times 0.766.643, and the force applied to the mass on the left is 1144.25 times negative 0.766, positive 0.643. So just multiply those numbers out. These are going to be in newtons, and that'll give you the components of those two force vectors. Okay, so that's it for number 19.